Here we are. At what distance will the electrically charged balloon magically or use its force to attract the Kleenex? That's what this standard's all about, you guys. Having fun with static electricity and with magnets. So, let's get started. Let's talk about those forces, why you can't push as hard as you can, and that force is there repelling each other. And when you flip your magnet to a different end, they attract. So, my standard is NGS S3 PS2-3. And it talks all about motion and stability with forces. And for this, it's about non-contact forces. So the standard itself says, ask questions to determine cause and effect relationships of electric or magnetic interactions between two objects not in contact with each other. So when you look into your academic language functions, you're going to use that cause and effect, or you're going to also look into analyzing why. So remember the 5 W's and the how. Who, what, when, where, why, and how. You know, what is creating this force to move? What distance can we get a better force? Or what distance will the force come? Why? If we use different magnets, can we attract bigger items or smaller items based on their strength? And how? How does it work? So with non-contact forces and with magnets, we've got a few terms here you want to know. Attract, which is going to pull or draw together. With magnets, you have your opposites attract, and repel would be to drive back or fight against, or repulse, they also say. So the way I like to explain this is opposites attract. Sometimes you get two different people and they get together and they have great conversation. And similar, the same way, if you have two forces that are the same, like your north ends of your magnets, a bar magnet has a north end and a south end. And if you put those two similar ends together, they're going to repel. So think about it as you have two people that are really strong leaders and they're both focused on stuff. And sometimes they butt heads and they just can't seem to attract. They really repel. So keep that idea in mind. Some of your safety measures with this lesson and standards are keeping magnets away from electronics. Nowadays with e-learning, virtual learning, we've got our electronics there. Not a good idea around your computers. If you have the good strong bar magnets, you're going to want to store them properly in your classroom. Make sure your students aren't dropping them because that can make the magnets less powerful or demagnetize them as they go. Also, make sure when they are attracting that you're not getting fingers pinched in there. Also, nowadays, a lot of students, you might not know it, but if they've got shunts, magnets aren't good around students' heads. You wouldn't want to mess with their shunt. Also be aware, if you're going to use balloons in the static electricity, be aware of latex allergies. You can also use wool to create electrostatic movement a lot of times. And this is a 3rd grade standard. Hopefully you don't have to worry about them eating magnets. That is a concern. If you want a down full run of all the other concerns, go to coolmagnetman.com and I'll show you how messed up your stomach will look if those magnets get eaten. So, but this is 3rd grade. We're not going to be eating magnets or hopefully not sticking them up our noses or in our ears. So, some of those questions that you're going to want to use as discussion as you fill out cause and effect and you're watching the forces that happen with magnets repelling and attracting or with the static electricity. Start to look at how does distance affect that attraction between these forces? And what if we used a stronger or a larger magnet? What would happen? And also remembering, not everything is magnetic. We only have certain things that attract. What happens when we increase the distance between the magnet and the object? Is it going to still have that chance to go ahead and attract or repulse? And what will the objects attract or repel from? How does the magnet orientation affect the movement? Because say you're looking at one end of the magnet and it's attracting, and then you flip it, and then maybe when you have the other end of the magnet, it's going to be repulsing, depending on that north or south pole that you're using on your magnet bar. And with the static, how much friction does one need to apply to create that the static electricity? I sat here with my balloon, rubbing my balloon on my hair, or you rub it on the wool piece of wool. How much more static do you need to create? How much friction do you need to make those electrons start to get heat up and moving so that you can make the water bend away? So some things with static electricity, it's pretty much your imbalance between negative and positive charges in an object. So hopefully all of you have had time to listen to a professor's video from this last week. If you took well notes on the electrons and the positive charges of those forces, that's going to help you a lot with the standard. So when you look at some of these pictures here, it'll show you. The first picture here kind of shows you some of your ideas. You can use static to charge a comb to pick up pieces of paper. You can see on here with the second one, it shows you how the objects with the same charge will repel each other. But yeah, if you statically charge a balloon, you can get it to stick to a wall because you have the opposite charges attracting each other there. Again, with magnets, your magnet field force exerts a force. And here you can see with the north and the south, it kind of shows you how one's pushing that force away and one's drawing that force in. So remember, we're just talking about those charges and these forces. And these forces, you don't have to necessarily, you can see these forces. Say when you have your magnets, you can see the forces coming together, or you can physically see that you cannot push these two magnets together because they are repulsing each other. So that's what we're looking at, is those non-contact forces. Bear with me here a moment. All right, some activities. You've probably done like the little girl has here, the balloon holding the electricity or the static, making your hair look all crazy. You can actually rub that balloon on your hair, or with a comb, rub your hair with a comb, and you can actually make the running water from your faucet bend. It was really neat. My daughter and I tried it out. Also paper clips. You can see not all paper clips work, but you can start to see at what point distance do they attract or not attract. I suggest if you do have a classroom where you're going to work on this and you're using magnets, try to get some good, powerful magnets. Magnets attract to iron, nickel, cobalt, so you could test stuff out. And I think, this could be a fun activity to channel your inner Jedi with the recent Mandalorian series. You can use your magnetic forces to create some force. Also, the hover plate's a great thing. If you've got 2 styrofoam plates, they can hover. I've got a static electricity video here that I will post on the Moodle along with in my document. So I encourage you, go out and check out this static electricity video. It just gives you some great ideas on how to you can move bubbles with static electricity. A lot of neat things there. So really, when you look at the motion and stability, the forces standards, you have the standard that comes before this. Asks students to start making those observation and measurements to predict the motion and the patterns we're seeing. And so then when you get to this standard, the 3PS2-3, we're trying to ask those questions. So we really start to think, what does the cause and the effect in the non-contact? And then the next standard that you kind of follow up with after this will have students using the magnets to solve a problem. So in my classroom scenario, I would focus on either static electricity or magnet. For my attention grabber, I might use a PVC pipe to go ahead and charge it with a wool cloth and move the soda can around. And then I can set up stations where students can pose the questions and they can fill in the cause and effect forms at each stations, doing like a foam plate, hover plate, the balloon with the water movement, make Rice Krispies dance, or picking up the, like I had the Kleenex where I picked up the Kleenex with the balloon. So, and then again, too, you can go ahead and work on some charts. I think kids always benefit from having charts in their classroom that show those motions. And as you can see, the standard really talks about the non-contact forces. And that's all, folks. I hope this helps you a little bit on magnets, and you can check out my document too. So have a wonderful day.